Hi, I'm Gilles Bonnet from the Ruhr University Bochum in Germany. I'm going to talk about weak convergence of the intersection point process of Poisson hyperplane. This is a joint work with Anastas Baki and Christoph Teller. We consider a stationary and isotropic Poisson hyperplane process. This will be formally defined in the next slide. Let's zoom out a little bit. We keep only the lines which intersect the ball of a given radius so that we have a finite number of them. We are interested in the intersection points, so let me erase the lines. You can still guess where they are because of the many alignments. Let's zoom out again. We now see all the points. This random collection of points is our main object of interest. We will also consider its convex hull at the end of this talk. If you only see this picture, you don't see much of the alignments, and it might be hard to believe that this comes from a collection of lines. But if you zoom in, the underlying structure appears again. Now I will define the Poisson hyperplane process we consider. It is stationary and isotropic, of intensity T, and restricted to the set of hyperplanes which intersect a ball of radius capital R. For this, we consider a Poisson distributed random variable capital N, which has parameter 2Tr. Next, we construct n IID hyperplanes intersecting the ball PR in the following way. We take U1, U2 until Un, IID unit vectors uniformly distributed on the unit sphere, and we take S1, S2 until Sn, n IID random numbers uniformly distributed between 0 and R. The hyperplane HI is defined as being orthonormal to the direction UI and at distance Si from the origin. The hyperplane process eta TR is the collection of the hyperplanes H1 until Hn. We define the intersection process Xi TR as being the set of all intersection of any d-tuple of hyperplanes in the hyperplane process eta TR. We are interested in asymptotic properties of the intersection point process Xi TR when the parameters T and R are such that the number of points goes to infinity. Is it possible to set the parameters T and R such that Xi TR converges to some point process? There is at least one way to do that. You fix the intensity T to be constant and you make the radius goes to infinity. You can think about it, this is pretty straightforward. What we show is that there is a non-trivial alternative where T goes to infinity and R is the function of T which goes to 0. The point process can converge only if the intensity measure converges. The intensity measure of a point process is a measure, here LTR, which evaluated in a set S gives the expected number of points of the process which are lying in the set S. By using a tool from integral geometry, here the multivariate Maker formula, we can represent this intensity measure as a multifold integral. By doing a careful analysis of this integral and using more tools from integral geometry, namely the Blaschke-Petkanchin formulas, then we are able to provide an approximation of the density of this measure. In particular, if capital R is equal to T to the minus D divided by T plus 1, it follows that for any fixed x non-zero, the density evaluated at x converges to the norm of x to the minus D plus 1 times a constant. This is the lemma that we have just seen. Let m be the measure on RT minus 0 with density constant times norm of x to the minus D plus 1. Then we will consider the total variation distance between the measure L and the measure M. But since the measure L has bounded density and the measure M has unbounded density, it explodes at the origin, we exclude a neighborhood of the origin. As a corollary of the above approximation, we obtain a bound on this total variation distance, and this bound goes to 0 as t goes to infinity. Therefore, a candidate for the limit of our intersection point process is the Poisson point process theta, which has intensity measure m. We will compare the intersection point process with the Poisson point process theta by using the Kantorowicz-Rubinstein distance. If you are unfamiliar with this distance, you can pause and take the time to read these few lines. Our main result is a quantitative bound on this distance under the assumption that the radius r is equal to t to the minus d over d plus 1. This implies, in particular, that the intersection point process psi tr converges in distribution to the Poisson point process theta. The proof relies on a theorem of Decrease, Schulte and Taylor, which, applied to our setting, provides a bound on the Kantorowicz-Rubinstein distance in terms of the total variation distance between the intensity measures of the processes and a collection of integrals, here denoted by capital I LT R of R. We have already bounded the total variation distance. Therefore, it remains only to bound these integrals, and this involves quite a number of steps, which I spare you for this presentation. For the last part of the talk, we will consider the convexel of the intersection point process. The convexel of the intersection process associated to a collection of hyperplanes has been studied already in several papers in the field of computational geometry. If you want to know more about that, I invite you to have a look at the references in our article. By applying the continuous mapping theorem to our main result, we obtain that the convexel of the intersection point process converges in distribution to the convexel of the Poisson point process theta. Similarly, the number of k-dimensional faces of the convexel of the intersection point process converges in distribution to the number of k-dimensional faces of the convexel of the Poisson point process. Now, by applying Fatou's lemma, we find that the lim_inf of the expected number of vertices of the convexel of the intersection point process is at least the expected number of vertices of the convexel of the Poisson point process. In dimension 2, thanks to a result from Kablushko, Marinich, Temesvari and Taylor, this is pi square over 2, which is strictly bigger than 4, which is the value conjectured by De Broglie and Toussaint, and therefore we disprove their conjecture. Thank you very much for watching this video. Here's the reference of our preprint. You can find there all the results I presented and more. If you have some questions, I will be very happy to hear them in the live discussion session. Thanks once more for watching, and goodbye.